Fingerprints are the most infallible means of identification. They assist in pinning down the criminal. Unfortunately, the criminals these days are well educated and they very well know that after committing the crime, if their fingerprints can be detected on any evidence removed from the scene of crime, they will be caught. So they endeavor to destroy the fingerprints or to rub them off before leaving the scene of crime. One of the most simple methods to do this is that after committing the crime, one can spray water on the crime scene. The fingerprints get washed away and then it becomes almost impossible to develop them. But then there are certain methods which under these adverse circumstances too can detect latent fingerprints. The most common of these is the small particle reagent technique. Small particle reagent is a suspension of molybdenum disulfide in a surface active reagent like detergent. It fixes the insoluble fatty acid constituents of the latent fingerprint. It's very obvious that when fingerprints are being developed on a wet surface, one has to target those constituents of sweat which do not get dissolved away. The fatty acids are one such constituent. They are insoluble in water. So if the criminal sprays water after committing the crime, nothing happens to the insoluble fatty acid constituents. This is not a chemical reaction. It is mere adsorption of the particles of molybdenum disulfide on the insoluble fatty acid matter in the latent fingerprint. We have tried to modify this method for one or two reasons. Firstly, molybdenum disulfide is quite costly. Secondly, it is dark in color, so it becomes almost impossible to visualize the fingerprints if the surface in question happens to be dark brown or black. And thirdly, molybdenum is a heavy metal and it is quite toxic. We have endeavored to replace molybdenum disulfide with zinc carbonate, which is white in color. And to that, we add a few drops of an organic dye. We can choose the dye depending upon the color of the background surface. If the background surface is blue, we can choose a yellow dye. If it is yellow, we can choose a black or blue dye, and we can vary the compositions to a large extent. We take care to add that dye which is fluorescent in nature, so that the weak fingerprints which are often encountered at the scene of crime can be enhanced, can be made more sharp by impinging ultraviolet light on them. Of course, we have to add the surface active agent also in this case, and it is normally any liquid commercial detergent like Gentile or Easy. This is in form of a suspension. One must first shake the bottle of the reagent, spray it on the crime scene, evidence, wait for about 1 minute and then dry it with a hair dryer. Depending upon the color of the dye, very sharp prints develop, and even if they are faint, even if they are weak, even if they are fragmented, as I said, they can be enhanced by impinging light from a suitable source, and generally we use long wavelength ultraviolet light for this purpose. This method is suitable for detecting fingerprints on non-porous surfaces, because the porous surfaces in water, they easily get degraded. Yet another method is the phase transfer catalyst method. Here we use a xanthine dye such as eosine or erythrosine in concert with a phase transfer catalyst. We normally choose tertiary tetrabutyl ammonium iodide as the catalyst. It brings a liaison between the insoluble lipid and fatty acid constituents of sweat with the dye. In this case also, very sharp prints develop, although there is one problem over here, and that is that the background surface tends to get stained. That problem doesn't crop up when we are using small particle reagent. But we have conducted experiments and we have seen that the phase transfer catalyst method works even if the crime scene evidence has been dipped in water for almost 30 to 36 hours. Yet another method is multi-metal deposition, where successively we deposit metals on such surfaces which are such constituents of sweat which are insoluble in water. This method is quite tedious, but then the advantage is that it works both on porous as well as non-porous surfaces. So whenever one encounters a crime scene on which water has been sprayed deliberately or maybe accidentally, any of these three methods can prove useful for detecting latent fingerprints.
Dear students, after studying this module, you shall be able to know that in the interest of solving crime cases, it is pertinent to standardize methods to detect latent fingerprints on such crime scene evidence that have been deliberately or accidentally wetted. Insoluble sweat constituents like lipid, proteins, and peptides. You'll also learn about that there are three techniques to detect latent fingerprints on wet items such as multi-metal deposition, physical developer, and small particle reagent. This module will teach you about each methodology for detecting fingerprints on moist surfaces has both merits and demerits. And you'll also learn that these techniques are being used for detecting latent fingerprints in actual casework investigations. A latent fingerprint is formed when the sweat pores of the papillary ridges leave a deposition of perspiration on the surface with which the finger has been brought into contact. Human body possesses the following three types of glands, that is, eccrine, epicrine, and sebaceous, the secretion of which contribute to a fingerprint deposit. Eccrine glands are widely distributed throughout the body and are particularly numerous on the palms of hands and the soles of feet. These glands secrete chemicals as a result of general metabolism and catabolism. Besides water content, eccrine sweat contains up to 1% of the other substance, of which inorganic salts constitute about one half. The other half is constituted by organic products like urea, keratin, choline, lactic acid, sugars, uric acid, amino acids, and proteins. Amongst the organic components of sweat, lipids, fatty acids, and peptides are insoluble in water. These are the ones that must be tagged if latent fingerprints are required to be developed on moist items. Such a situation arises if a criminal, after committing an offense, sprays water on the crime scene so as to wash out the finger impressions. If the crime scene is outdoors, there are chances that natural factors like rainfall and humidity may degrade the fingerprints. Under such circumstances, it is pertinent to call into action those techniques that can detect latent fingerprints on crime scene evidence removed from such despoiled sites. Now let us see methodologies for detecting fingerprints on wet surfaces. There are three main techniques to detect latent fingerprints on wet crime scene evidence: multi-metal deposition, physical developer, and small particle reagent. These are discussed in sequel. Let us start with multi-metal deposition technique. Multi-metal deposition is a versatile technique of detecting latent fingerprints on porous items, for example, fabric tape, masking tape, cardboard, on semi-porous items, for example, expanded polystyrene, latex, gloves, waxed paper, as well as on non-porous items, for example, metals and plastics. It is also named because it is a two-step process, the first involving deposition of gold and the second deposition of silver on the ridges, thereby visualizing the latent impressions. Now let me tell you about the mechanism. It has been known since long that colloidal gold particles adhere to amino acids, proteins, and peptides. The multi-metal deposition technique of fingerprint development relies on the affinity of gold particles for these biomolecules as the latter are present in fairly large concentration in sweat residue. The methodology is a two-phase process. In the first phase, colloidal gold particles adhere to the amino acid, protein, and peptide content of fingerprint deposition, while in the second phase, silver particles get adsorbed on gold layers, improving the contrast. The process was adopted from a sensitive amino gold silver staining procedure, whereby the secondary colloidal silver deposition step improved the labeling of proteins. The colloidal gold particles are produced by the reduction of hydrogen tetrachloroaurate 3, commonly referred to as tetrachloroauric acid, by citric acid. The working solution of multi-metal deposition method also contains sodium citrate. The citrate anions furnished by sodium citrate engulf the colloidal gold particles and impart a negative charge to these. The amino acids or their fragments in proteins and peptides under neutral conditions exits as zwittrions. However, under acidic condition, the amino acids acquire an overall positive charge. Citric acid brings the pH of the working solution in 2.5 to 2.8 range, thereby inducing a positive charge on amino acids present in sweat residue. Thus, the colloidal gold particles bear a negative charge, and the amino acids bear a positive charge. The electrostatic attraction between the two chemical entities is responsible for the adherence of gold particles on amino acid, protein, and peptide content of the sweat residue. It is pertinent to state that citric acid performs two functions. Firstly, it reduces hydrogen tetrachloroaurate ion to colloidal gold, and secondly brings the pH of the working solution in the desired range. The gold particles adsorbed on amino acid, protein, and peptide content of fingerprint residue do not impart a pronounced color to the ridges. Nevertheless, these provide a site for the nucleation of silver particles. The latter are produced by the reduction of silver ion by silver 2 ion. Being a reversible reaction, there are chances that it may proceed from right to left. However, the citrate ion complex with iron 3 ions and remove these from the equilibrium system, pushing the reaction to the right. The silver particles then settle on the colloidal gold, imparting a dark gray or black color to the ridges. Preparation of reagent. The process of developing latent fingerprints by multi-metal deposition technique begins with the preparation of the following solution. Solution A contains 1 gram hydrogen tetrachloroaurate in 10 ml distilled water. Solution B contains 1 gram sodium citrate in 100 ml distilled water. Solution C 1 ml polyethylene glycol in 100 ml distilled water. Solution D 4.8 gram citric acid in 50 ml distilled water. Working solution 1 or the colloidal gold solution is prepared as followed. Place 1 ml of solution A in about 950 ml distilled water. Mix thoroughly and heat to gentle boiling. Add 15 ml of solution B and continue to boil till the content acquire a port wine color. Turn off the heat source and while the mixture is still hot, add 5 ml of a liquid detergent. Agitate to mix the contents thoroughly. Cool and add 10 ml of solution C. Adjust the pH to 2.5 to 2.8 by adding 1 to 1.5 ml of solution D. Make up the volume 2000 ml. Store the working solution 1 in an absolutely clean vial in a refrigerator. Next, the following solutions are prepared. Solution E is prepared by mixing 20 gram silver nitrate in 100 ml distilled water. Solution F is prepared by 16 gram ferric nitrate, 44 gram ferrous ammonium sulfate, 11 grams citric acid, and 0.25 ml liquid detergent in 1000 ml distilled water. Working solution 2, or the modified physical developer solution, is prepared by adding 10 ml of solution E to 990 ml of solution F. Agitate to mix thoroughly. The shelf life of the solution is just 15 to 20 minutes, and therefore it should be formulated immediately before processing the items for developing fingerprints. Now let us see process for development of fingerprints. Latent fingerprints are developed by the following procedure. Number 1. The item bearing latent prints is placed in a tray and covered with distilled water. The tray is rocked gently by using a shaker. The item is placed in another tray to which working solution 1 is added. The tray is shaken for 30 to 45 minutes. If more than one item is placed in the tray, these are not allowed to overlap. The item is taken out of the working solution 1 and rinsed with several batches of distilled water, faint fingerprints being to appear. The item is then placed in another tray and working solution 2 is poured over it. The solution is agitated for 5 to 15 minutes. The item is washed with water several times till the washings are no longer yellow and turbid. The developed fingerprints, which are dark gray or black, are photographed. The item is allowed to dry under natural conditions and thereafter the prints are lifted with the aid of fingerprint tape. Now let me tell you the assessment of multi-metal deposition technique. Multi-metal deposition method detects latent fingerprint on a host of surfaces: porous, semi-porous, and non-porous, moist and dry. These include paper, glass, adhesive tapes, and plastics and polymers. Blood prints too may be enhanced by this technique. However, multi-metal deposition suffers from a number of shortcomings too. It is a costly and complicated procedure involving several steps. Moreover, it did not give satisfactory results on cartridge cases and interfered with subsequent analysis of firearms. Now let us talk about physical developer technique. The physical developer technique is a means to detect fingerprints on dry and wet porous items including paper, articles, clay-based products, and adhesive tapes. The process involves an oxidation reaction coupled whereby a solution of an iron salt reduces aqueous silver nitrate to finely divided metallic silver. The technique derives its name from the photographic physical developer, which during processing the film roll undergoes a similar redox reaction. The physical developer reveals the fingerprints as dark gray or black images due to adsorption of metallic silver particles on the fatty acid and lipid components of sweat residue. Now let me tell you about the mechanism. The basic of the physical developer technique is the in situ reduction of silver 1 ion to colloidal elemental silver, which in turn interacts with the organic constituents of the fingerprint residue and ultimately visualizes the impressions as dark gray or black ridges. The same redox reaction is involved in the development of photographic films. The physical developer composition is a mixture of the following components. Number 1, an aqueous solution of silver nitrate. Number 2, an iron 2 and iron 3 redox couple. Number 3, an acid buffer, usually citric acid. Number 4, a ketonic detergent, usually N-dodecyl amine acetate. The iron 2 ions reduce silver 1 ions to metallic silver and simultaneously gets oxidized to iron 3 ions. Due to the reversible nature of this reaction, the chances are that iron 3 ions may reoxidize metallic silver to silver 1 ion. To overcome this problem, citric acid is added to the fingerprint composition. Citric acid complexes with iron 3 ions are removed these from the equilibrium system, thereby pushing the redox reaction in forward direction. It also brings down the pH of the composition. This is important since optimum results are obtained under mildly acidic conditions. The finely divided metallic silver particles formed as a result of the redox reaction are colloidal in nature. It is in this state that these adhere to the fatty acid and lipid constituent of the latent fingerprints and visualize the impression. However, if the concentration of metallic silver increases beyond a threshold, the particles coalesces and precipitate out. The colloidal nature of silver particles is lost and the quality of developed fingerprints tends to fall. This problem is taken care of by incorporating a ketonic detergent, usually N-dodecylamine acetate, in the fingerprint composition. The cations engulf silver particles, imparting a positive charge on to these. The positively charged particles repel each other, thereby averting the possibility of their coming close and condensing into a precipitate. This phenomenon is called peptization and is symbolically shown in the figure. Let us talk about pre-treatment of latent fingerprints. The physical developer technique works very well on paper and paper products. However, the finished paper usually incorporates alkaline fillers and binders. These react with the physical developer composition and alter the concentration of its ingredients. It is therefore pertinent to neutralize the alkaline content of paper before attempting to develop fingerprints. This is carried out by giving an acid pre-wash to the paper sample. Malic acid is commonly used for this purpose. A solution containing 25 g malic acid in 1 liter of water is prepared. The paper item is dipped in this solution for 5 to 10 minutes till the bubbles cease to evolve. Let us talk about the methodology. The following three solutions are required for detecting fingerprints by physical developer method. Number 1, solution A or the detergent solution. It is prepared by dissolving 0.23 g N-dodecylamine acetate in 40 ml distilled water. Solution B or the redox solution. It is prepared by adding successively 30 g iron nitrate, 80 g ammonium iron sulfate or more salts, and 20 g citric acid to 900 ml distilled water. Solution C or the silver nitrate solution. It is prepared by dissolving 10 g silver nitrate in 50 ml distilled water. This solution is stored in a dark place. The working solution is prepared as follows. Solution A is added to solution B. The mixture is stirred for about 2 minutes. Thereafter, solution C is added and stirring is continued for another 1 to 2 minutes. Before proceeding further, the authenticity of the working solution ought to be checked by the following test. A drop of dilute gold chloride solution is spotted on the Watsman filter paper. The latter is immersed in the working solution. If the spotted region gets darkened with 3 to 5 seconds, the solution is appropriate for use. Otherwise, a fresh lot must be prepared. The working solution is next added to a glass tray, which in turn is mounted on an electric shaker. An object bearing the latent fingerprint is immersed in the working solution, which is then gently agitated by the shaker for about 15 minutes. The tray should not be overloaded with samples. Preferably, only one item should be processed at a time. Dark gray or black colored fingerprints develop. The object is thoroughly washed by immersing it in distilled water for 5 minutes. The washing operation is repeated twice more, each time with a fresh batch of distilled water. Assessment of physical developer technique. Physical developer is a sensitive method of detecting fingerprints on porous items. It is specifically useful when fingerprints are required to be visualized on articles which have been deliberately or accidentally wetted. Under these conditions, the amino acid constituents of sweat residue are easily washed out and ninhydrin method fails. Nevertheless, physical developer yields results. The sensitivity of the composition may be enhanced by pre-treatment or post-treatment methodologies. However, the requirement of a relatively large number of reagents make the technique cumbersome and expensive. Now let us talk about small particle reagent technique. Small particle reagent technique is used to detect latent fingerprint on non-porous crime scene evidence, including those that have been accidentally or deliberately wetted. Conventional small particle reagent is formulated by suspending a finely powdered, insoluble binary salt, usually molybdenum disulfide or titanium dioxide, in water containing a few drops of surfactant. A commercial liquid detergent is generally used as a surfactant. The insoluble salt adheres to the fatty components of the sweat residue. The small particle reagent technique is also referred to as wet powdering. Now let us have a look on its significance. The most common base material used for formulating small particle reagent is molybdenum disulfide. It is an insoluble binary inorganic salt of dark gray shade. When suspended in water containing a few drops of surfactant and applied to a latent impression, this salt gets adsorbed on the sebaceous constituent of sweat residue. The salt is pulverized before preparing its suspension, and hence the technique is often referred to as wet powdering. The particle size in the range 1 to 10 μm is deemed appropriate for detection of latent impressions. The crystallized structure of molybdenum disulfide too is critical for developing optimum quality fingerprints. Base materials like titanium dioxide, cobalt oxide, graphite, and photocopier toner may substitute for molybdenum disulfide. The sebaceous sweat largely contains fatty acids, lipids, and glycerols derivatives. These biomolecules are quite stable and retain their composition in latent fingerprints for relatively long periods. Moreover, these are insoluble in water. For this reason, small particle reagent is able to detect fingerprints on those items which have remained immersed in water for varying time periods. The method has been used to detect fingerprints on vehicles wet with rain or on glass, metal, and plastic items recovered from aquatic systems. It has also been used to develop fingerprints on water-soaked firearms. The detection process does not interfere with subsequent ballistic analysis. The small particle reagent method has also been used to detect latent fingerprints on raw ivory articles. In addition, it works on plastic bags, wax paper glass, and painted utensils. Small particle reagent method works on containers which become contaminated by the commodity they hold. For example, soft drink cans and glasses are often wetted by the beverages. Regular powders fail to detect fingerprint on such surfaces, but small particle reagent technique gives result. The powder method often fails to develop fingerprints on items which have a rough texture or an irregular shape. The reason is that the powder cannot be brushed to every nook and corner of such a surface. Yet, when the article is treated with a suspension, either by dipping or by spraying, the composition touches every segment of the surface and the chances of detecting fingerprints are far greater. The molybdenum disulfide based small particle reagent has been successful in lifting latent impressions from glass bottles coated with arson accelerators including gasoline, diesels, turpentine, oil, and thinner. The surfactant, also called as surface active agent, is an important component of a small particle formulation. It has two functions. Firstly, it delays the sedimentation of the insoluble salt. Secondly, the more importantly, it ensures a uniform application of suspension on the surface. Usually, a commercial liquid detergent serves as a surfactant in small particle reagent formulations. Its concentration in the composition is critical to optimum development of fingerprints. If it is too little or too excess, the quality of prints is lowered. The fingerprints developed by molybdenum disulfide based composition are dark gray in color. Proper contrast is not achieved if the background color of the surface too is dark. For such surfaces, molybdenum disulfide is replaced by titanium dioxide. Since titanium dioxide is white in color, it gives a good contrast on dark surfaces. In fact, the titanium dioxide based composition gives clear and sharp fingerprints on adhesive materials. Now let me tell you something about the methodology. Small lots of molybdenum disulfide are added to water and a commercial liquid detergent. For example, Gentile or Easy, the suspension is agitated and transferred to a tray or a spray bottle. The surface bearing the latent fingerprints is either sprayed with or dipped in the small particle reagent formulation. On vertical surfaces, the reagent is sprayed directly above the region where fingerprints are likely to be present. As it drips down, it covers the latent impression. It takes 1 to 3 minutes for the fingerprints to develop. Thereafter, the item is washed under a gentle stream of water for about 30 seconds to remove the excess material. The developed fingerprints are photographed. These are then allowed to dry either under neutral conditions or with the aid of a hair dryer. Finally, these are lifted by using a fingerprint tape. An advantage of a small particle reagent technique is that after the fingerprints have been photographed and lifted, the surface may be rendered clean by wiping with moist cotton. No permanent stains are left on the surface after impressions have been developed. Now let us start with the assessment of small particle reagent technique. Small particle reagent is an efficient and sensitive technique to develop fingerprints on wet non-porous items. It gives good result even on dry surfaces. The method is very simple and may be operated even by an amateurish hand. Now, dear students, let us summarize this chapter. So, in this chapter, we have learned that the three techniques, which are multi-metal deposition, physical developer, and small particle reagents, outlined in this module, serve to detect latent fingerprints on wet crime scene evidences, whereas the multi-metal deposition and physical developer method are used mainly for porous items. The small particle reagent works on non-porous articles. The multi-metal deposition and physical developer procedure are cumbersome and time-consuming. Both involve a large number of steps as well as large number of reagents. Moreover, the methods are expensive. Lastly, we have learned that the small particle reagent technique, on the other hand, is simple to operate. It requires a fewer reagent, gives quick result, and is cost effective.